an update for 2025?
Actually, there is an update for 2025, but this isn't my title. I sent you my title a long time ago. It was a Seifert dream. That is my title. This is something else. This is, so you see, this is the subject I really like to talk about, but I've talked about it too many times, and people have heard it already. Also, it's on YouTube. You know, you can watch it elsewhere. So on the other hand, it's the preliminary for what I want to talk about. So I'm going to give 2 talks today with a 3-minute intermission in between. One will be this 1-hour talk from Toronto, which I will condense to 20 minutes, or 25, I don't know, whatever it will be. And therefore, in the handouts that you have, only the green stuff I'm going to cover, and I'm going to ignore all the proofs and so on. Then there will be a 3-minute intermission, and then I will completely change pace, and instead of talking about that, I will talk about today's talk, and it will be a much dreamier and a completely different topic. So, okay, that's the plan. Now, oh, I should have started the timer. Okay. Good. So, yeah, my talk follows a handout. As I said, I will, for the earlier topic, I will only do the green stuff. And the title of the old talk, the one from Toronto and from, actually I also gave it at UCLA, has the word strongly, genuinely computable. So I want to explain what these terms are. So there is a certain invariant theta that Roland van der Veen and I are computing, and I want to explain what I mean by strongest. So if you compute it on prime knots, basically the kind of extension of the Rolfson table, the Hoste table, then you find that actually that table has 249 knots with up to 10 crossings, and if you go down the table, it has 313,230 knots with up to 15 crossing. And then you try to evaluate how strong are various invariants. So if you take Chobanov homology and the Homfly polynomial together, then with knots up to 10 crossings, and you compute this pair, or knots with up to 10 crossings, you find that it attains 248 distinct values, which means that there is a deficit of 1. And if you look at this invariant theta that I'm about to tell you about, the deficit is 0. You get 249 different values, so it's better. But then if you increase the crossing counts, then the deficit for Chobanov homology and the Homfly polynomial taken together is 70,000, whereas for the invariant I'm going to tell you about, the deficit is only 6,700 something. So in some very loose sense, it's 10 times better. Okay? So, so that's the meaning of the word strong. Now, what do I mean by genuinely computable? So, you can compute it with knots with hundreds of crossings. In particular, I'll explain it in a minute. Here is the value of the invariant on a random knot with 300 crossings. For basically, and for practically anything else in knot theory, if you say 300 crossings, it's science fiction. Okay, you cannot compute basically anything. So that's what I mean by genuinely computable. And I should also say that it's fun, and let me justify the word fun a little bit. And part of the justification is that there is a lot about it that we don't understand, And from a mathematician's perspective, that's kind of the definition of fun. It means that other people, you can work on it and do things. But also, let me explain what these pictures mean. So the invariant is actually an ordered pair, a one-variable polynomial and a two-variable polynomial. A one-variable polynomial is a list of coefficients. And you can think of the coefficients as determining color values. So say positive coefficients are red and negative coefficients are blue. And if it's a big positive number, it's kind of darker red. And if it's a small positive number, then it's a very light pinkish red. Okay? So if you do it to a one-variable polynomial, you get a barcode. And our invariant is an ordered pair, so a one-variable polynomial and a two-variable polynomial. So at the top is the barcode. Okay, it's not very exciting. It just alternates colors. Also, it's just the Alexander polynomial. The two-variable part, which we call lowercase theta, is a two-variable polynomial, and so you can think of it as a two-dimensional array of numbers. But a two-dimensional array of numbers is a two-dimensional, right, these are the coefficients. So it's a two-dimensional array of color values, or color values for each pixel. So it's a picture, okay? And this is the picture for that 350, for that random 300 crossing knot. So I'm slightly lying. The picture, the way I printed it, looks like a hexagon. The actual picture looks like, well, a hexagon too, but sheared. And what I do is, so as to expose the symmetry, to highlight the symmetry, we shear the hexagon. We just apply a shear transformation to the plane. So instead of the picture being bounded in a shape like that, it's bounded in a shape like that. Okay? So that's the two-variable part of the invariant. There are patterns here. I really don't understand the patterns. In fact, we can't even prove that it's a hexagon. Okay? But there are more. So here are some random knots with 101 to 115 crossings, just the two-variable part. Again, you can see patterns. I don't understand them. Here is the so-called Rolfsen table. So all nodes with up to 250 crossings. Again, you can see patterns. I don't understand them. Here are some torus knots. It's a slightly different pattern. Yeah?
Are you also standardizing the size of the picture?
Yeah.
And
I mean, I'm shrinking.
With more crossings, it gets bigger?
Yeah, so what?
With more crossings, is the diameter bigger of that?
Well, no, I'm shrinking the pixels. So with more crossings, I get, the picture is always of the same, so
Yeah.
the pictures for the Rolfsen table are always of the same size.
Right.
But like if you look at 3.1 up at the top, you can actually see the hexagons, the individual pixels. And if you look at like large knots, it's quite hard to see the individual pixels.
Okay.
So the gaps
Yeah.
are like zero.
Sorry?
So there are some gaps there.
There are some gaps because the two-variable polynomial sometimes vanishes. But if you add to it the one variable, it actually separates all nodes with up to 10 crossings. And in fact, if you look very carefully, you'll see that like the gap here looks the same as the the barcode up here looks the same as the barcode that's up there. Actually, the shades are infinitesimally different, and so that's a failure of our eyes. Okay? Anyway, here are some torus knots. Here is the 22/7 torus knot, just for fun. And that's it. Now let me tell you how to define this invariant. Okay? So first of all, conventions T, T1, and T2 are indeterminates, just variables. And T3 is defined to be the product of T1 and T2. Now given a crossing, you paint the color, given a knot. I told Nelson before that I'm somehow not in the mood. I hope I'll get it. I hope I'll go through it somehow. Anyway, given a knot, you put it in the plane in a certain way. That doesn't really matter. And then you color the crossings, just so you'll see in a minute why. And then you number the edges. So the edges are numbered 1, 2, 3, 4, 5, 6, 7. I hope you can see that. And there is also some marking for rotation numbers, but let me ignore that because it's like for the 1 hour version. And then you use this to make a matrix. So, for example, the yellow crossing has 2 strands. The incoming upper strand is labeled 3. The incoming lower strand is labeled 6, and it's a positive crossing. And then I have a rule which says that if I have a crossing of sign S with incoming upper strand I, incoming lower strand J, then it contributes to the matrix a contribution at row I, row J, column I plus 1, column J plus 1, a certain 2 by 2 contribution. So you start with the identity matrix. So you let A be the 2n plus 1 by 2n plus 1 identity matrix. And then for each crossing, you add a 2 by 2 block like that. When you do it for the trefoil example, you get the identity matrix. You can see the ones on the diagonal. And then from the yellow crossing, you get these 4 contributions. From the purplish crossing, you get 3 other. Well, it's clear what you get, okay? So this gives you a matrix. In the case of the trefoil, it's 7 by 7. And then the next thing you do is you invert this matrix, and you call the result G. Okay? Now, people, you know, writing the Skene relation for the Kaufman bracket is way easier. But in practice, computing the Kaufman bracket is an exponential time computation. Inverting a 7 by 7 matrix is something that all of us dread, but in fact, it's really, really easy, computationally speaking. And, you know, there are no programs that can compute the complete Kaufman state sum of 100 crossing knots, but there is no problem inverting a 100 by 100 matrix. Okay? So, so this is actually easy, even if it doesn't look like it. Okay? And then you do the following. So first of all, okay, so you let, maybe this is missing here, but you let G, okay, maybe I will write it here. You let lowercase g nu alpha beta be the matrix G in position in row alpha and column beta, subject to the rule, this is not division, this is apply the rule, that the variable t becomes the variable t sub nu, where nu is 1, 2, or 3, and I remind you that 3 is the product of 1 and 2. So these are these G nu alpha betas, and then you form a sum. So the invariant theta, the 2-variable polynomial, is a certain sum of 3 contributions. One contribution is a sum, or the first one is, a normalization factor, and then a sum of 3 contributions. The first one is a sum over crossing, and for each crossing, well, each crossing has an I and a J, and also a sign, but for each crossing, you look at some quadratic formula made out of these G nu alpha betas. Okay? And then the second summand is a double sum over pairs of crossings. And if you have a pair of crossing, it has two ij pairs, so I0, J0, I1, J1, and then the formula is a certain cubic formula in the G nu alpha betas, where alpha and beta are among I0, J0, I1, and J1. And then there is a normalization thing that I don't want to talk about. But it's roughly the same. Now, that looks terrible. But again, if you're a computer, you don't care. Because a double summation over the knot is just quadratic time. That's nothing. And evaluating a polynomial in the entries of the matrix that you've already computed is also nothing. So this is extremely efficient to compute, even if it doesn't look like it at first sight. Anyway, here are those polynomials. Here is R11 of a crossing. Here is R12 of a pair of crossings, sine S0, I0, J0. S sine, the second crossing has sine S1 and inputs I1 and J1. And you get a certain specific polynomial in these G nu ij's, okay? And again, I have nothing particularly nice to say about these polynomials except that it works, okay? And in fact, implementing this is a complete triviality. So here is the full program. So I let CS, this is the list of crossings. And it's obtained by some external programs that converts whatever format you have for the knot into a list of crossings of the form. Each crossing is of the form Sij. I'm ignoring phi. The phi is the rotation numbers, and I'm ignoring it at the point. It's a minor normalization issue. Then I let A be the identity matrix of size 2n plus 1. Then, for each case within the list of crossings, for each case of instance of something of the form Sij within the list of crossings, I take the matrix A at rows I and J and columns I plus 1 and J plus 1. I wish I had a better pointer, but anyway, I am here. And then I add to it exactly the block that I mentioned before. Then I compute the determinant of A and normalize it in a certain way and call the result delta because it's actually the Alexander polynomial. Then I let the G be the inverse of A, and then I add to theta a double sum of R12s, a single sum of R11s, and the normalization thing that I don't want to talk about, and eventually I output theta. Okay, so it's really an easy program, and as I mentioned, it runs, it works. You can run it or not with up to 300 crossings. Okay, and then the last thing I want to say about this invariant is that it's meaningful. So it's topologically meaningful. So conjecture, and this conjecture is true. I mean, there is no, sometimes conjectures are speculative, sometimes you don't really know, okay? But this conjecture has both theoretical support and experimental verification to a very high order. So there is no question that it's true, okay? It's just, it's not yet proven theorem, okay? Anyway, the conjecture is that for any knot K, there is a genus bound. Basically, this the degree of the theta invariant is always. Oh my God! Did I mess up the what? It's the other way.
Yeah, because we have examples where it's zero.
Yeah. It's of course the other way. Sorry, the inequality goes the other way. Sorry. So the degree of this polynomial theta is always less than the genus. So theta must know something about Seifert surfaces. And then on my standard talk on the topic, which I've given at UCLA and Sukarit attended it, and it's also on YouTube, I say conjecture, theta has another formula. This is conjecture 7, which is which somehow sees the Seifert formula, the Seifert surface, which somehow starts from the Seifert surface. And that other formula is the content of my second talk today, which I will start after a 3-minute intermission. So it is now 4:04. I will continue at 4:07.
Can we ask questions in the meantime?
Yeah, but they're not formally a part of my talk. You can ask me about my love life.
Can I ask where you came up with this, how you were inspired? Like, where does this come from? You mentioned them.
So it has history. It comes from the so-called two-loop contribution to the Kontsevich integral. It comes from quantum algebra in a very, very roundabout way. I'd rather talk about my love life. No, it's not so. I can't answer in 2 minutes. Sorry, I'm just starting my timer.
Yeah, so I liked your conviction that conjecture 6 is really a theorem.
Yeah.
Do you share that kind of conviction with, say, that the Jones polynomial detects the unknown?
Oh no, that's different. The Jones polynomial detects the unknown is a kind of a low probability. You know, it's completely. How should I say that? You're making a statement about something non-generic. Okay, so maybe there is some 200 crossing knot whose Jones polynomial is zeros. There is no, or.
I was kind of trying to figure out how you would contrast.
No, this is different. So okay, when you compute the Jones polynomials of the knots of the on the Rolfson table, and all of them come out non-zero, that's not a surprise at all, right? Because there are so many polynomials, why would they come out zero? Okay, but when you compute this invariant theta on each knot is an actual verification of the conjecture. Each computation, if the degree is less than the genus, is a further verification of the conjecture. It's not a probability nearly one event. It's something that could be true or false for each individual knot. Also, there is theoretical reasons to think it, but. Yeah, sorry.
Okay. Isn't it strictly less than the genus, or could it be equal to the genus?
I don't remember, and given that I made a mistake there, a typo, I'd rather check before writing. It's either less or less than or equal. I was very careful putting the ceiling over there, right? But I wasn't. Yeah, but this is silly. Okay. Anyway, I think the intermission is over. So let me start with my second talk. So this is completely different style, okay? I'm talking about a dream, okay? So the dream is that there is a formula for the invariant mentioned before, which you can read from a Seifert surface of the knot. So let me explain a few things. First of all, here is a sculpture that I saw in Mexico City, and it's just a picture, so you don't have to pay any tariffs to bring it into the great United States of America. It happens to be a Seifert surface of a trefoil knot. So the boundary of this picture is a knot. So if you look at the boundary of this two-dimensional surface, it's a knot, the edge, and the surface itself is an orientable surface whose boundary is that knot. Now, if you have a Seifert surface of a knot, you can define the so-called Seifert pairing on the homology of that Seifert surface. So suppose you have two homology classes in on the Seifert surface, in the Seifert surface. So the green homology class, which is just a loop, and the purple homology class, which is just another loop. Okay? What you can do is you can compute the linking number of the green class with the purple class, except that the purple class may intersect the green class, and then there is no linking number. So what you do is you push the purple class a bit outside of the Seifert surface in the direction specified by the orientation. So basically, you can see it, if you look carefully at the picture, you can see that P, the purple class, is actually floating outside the Seifert surface, just above it, okay, or just above the surface, okay? And in this case, this isn't a particularly nice example because the linking number comes out to be 0. Okay, the linking number of green and purple is 0. However, had I computed the linking number of P minus and G, or alternatively of P with G plus, it would come out 1 or minus 1. So this number is not always 0. Anyway, the Seifert formula for the Alexander polynomial is the following. So first of all, you define a quadratic form Q defined on two classes, P and G, where P and G are in H1, by, well, it's T to the 1/2 the linking of P plus with G, plus T to the minus 1/2, oh, did I blunder again and it's minus? It's minus. Sorry, I blundered again. So it's minus T to the minus 1/2, the linking number of P with G plus. And a quadratic form can be represented by a matrix, and then you compute the determinant of the matrix, and I'll short it to the determinant of the quadratic form. And the claim is that the Alexander polynomial is the determinant of that quadratic form. Now, determinants of quadratic forms also occur in another place. Namely, you can integrate the exponential of the quadratic form over twice H1, twice the first homology of the surface. So one integral is dp, the one integration variable I'll call p, and the other I'll call x. And strictly speaking, this integral is divergent, but you can make it convergent, for example, by putting an I in front of the Q, and then you'll get a formula for the answer, and the formula for the answer is 1 over the determinant of the quadratic form, with some factors of i's and things, okay, and pi's, okay? So with the understanding that I completely ignore factors of I and factors of pi and factors of 2, the integral of the exponential of the quadratic is 1 over the determinant of that quadratic. And so if your quadratic is the quadratic given above, then that's a formula for the Alexander polynomial. Okay?
George, what is
It's
this
of course, what?
2 times h1 of sigma? Is this h1 cross?
Oh, it's H1 direct sum itself, because I have two variables, P and X, and both of them live in H1.
Okay, so like you were doing like 6 times h1, so that was a h1 to the 6th power.
Yeah, yeah. So it's 6 powers in the additive sense, not tensor power. It's direct sum. Okay? By the way, it's a useless formula because why would you ever want to integrate if you can compute the determinant? I mean, integrating something over a high-dimensional space is practically impossible, right? There is the curse of dimensionality. It's not what you want to do, but it's still an inspiration.
Question.
Anyway, yes.
And as like dp and dx, that seems to suggest there's some like position and momentum interpretation of this.
Yes, so it came from some.
Okay.
Yeah, that's the history. You're right.
But which one's the position and which one's the momentum?
It doesn't matter. At this point, it doesn't matter. At this point, these are just names of variables. Okay? Anyway, okay. So, after Gaussian integrations, there is something called perturbed Gaussian integration. And this is when you try to compute the integral of something which is the exponential of a quadratic plus a perturbation, and the perturbation is supposed to be small relative to the quadratic, so it's supposed to be somehow multiplied by epsilon. Okay, so there should be some constant epsilon appearing there. Okay? And I will call the perturbation docile, basically if, so this perturbation is also a polynomial in the integration variables. Let's call them x1 through xn right here. And I will call the perturbation docile if the degree in the x variables is bounded by some function of the degree in epsilon. Okay? And then the theorem, which I will attribute to Feynman, but it's a complete historical lie. So basically, Feynman did path integrals, and path integrals are infinite dimensional integrals. And when you and he found that you can compute them by reducing them, you can compute their perturbative expansion by reducing it to finite dimensional integrals. So he went from infinite dimensional integrals to finite dimensional integrals. But it turns out that if you run the exact same procedure on finite dimensional perturbed Gaussians, it reduces the computation to sums, to zero-dimensional integrals, which are sums. And furthermore, these sums are computable in polynomial time. So I'm attributing it to Feynman because I don't think there is anybody else you can attribute it to, but Feynman would have laughed if he had seen this. So anyway, the claim is just as written here. So if you have a quadratic in n variables, x1 up to xn, and you have a docile perturbation, then the power series expansion in epsilon of the integral, which is of course a function of epsilon, can be computed in polynomial time. And in fact, the result of the computation is that z epsilon, let's do the short people's trick. Z epsilon is the determinant of the quadratic part to the -1/2 multiplied by something. So I just move the determinant to the 1/2 to the left. So the determinant to the 1/2 times z epsilon is equal to the following thing. The following thing is the complete pairing of the differential operator written here with the polynomial or power series written here. What is the differential operator? Well, you take the quadratic form, you invert it. Now it's a quadratic form on the dual space, and everywhere where you had, and you use for the dual variables of the xi's, you use differentiations with respect to xi's. So you get e to some quadratic operator in d to dxi. And the exponential of p epsilon is just a power series in epsilon and the variable and all the other variables. But remember that the degree of the other variables is bounded by some function of the degree in epsilon. So if you look at x p epsilon up to degree 5, say in epsilon, then the degree in all the other variables will be bounded, will be at most 17, okay? And then the complete pairing of a differential operator with a polynomial is you just apply the differential operator to the polynomial and substitute all the variables to 0 afterwards. So basically, each derivative picks a variable x and kills it. And if there are any variables x's left afterwards, the expression goes to 0. So here is a visual way to see it. So the exponential of, so basically Q inverse of the derivative with respect to x is like a quadratic differential operator. So it has two sharp things that differentiate things. And they come with coefficients that are proportional to Q inverse. Okay? And if you exponentiate it, you get several copies of that two sharp-ended thing. Okay? And then P epsilon is a polynomial. Say it's a cubic polynomial. So for the sake of the picture. And then you get well, I'll imagine a cubic polynomial as something with three things that can be differentiated. And if I exponentiate it, I get multiple copies of that pitchfork. Okay? And then the complete pairing is just the sum of all ways of connecting the derivatives to the x's. Each derivative kills one x, and you can do it in all possible ways. So, and in fact, if you look at this picture, then these connections at the end look like graphs, and these graphs are the so-called Feynman diagrams. But the point is that this can be computed really efficiently because basically, let's do the worst imaginable case. So this is one of the x variables, there are n of them. This is one of the x variables, there are n of them. So there is n to the 6 choices or possibilities for what would appear here. And n to the 6 is still polynomial in n. So if you look at the low degree or low power of epsilon part of z epsilon, then you end up looking at a polynomial time computation. Oh my God, I'm sorry, this is so vague. That's the nature of dreams, they're dreaming. No, but this is completely rigorous. This isn't the dream yet. The point is that the invariant theta, in fact, comes from such a computation. Now, the thing that gets integrated, the so-called action functional or e to the Lagrangian, whatever, is too complicated to put on one slide for theta. So instead I'm showing you theta evaluated at t and 1. Okay? Basically, in that case, you end up integrating on, so you end up doing a so-called, a Gaussian integral, that's the g here, and you integrate it over twice the space of edges of the knot, because if you remember the formulas for thetas, they were around edges. They were centered, they were edge-centric. So you integrate over twice the space of edges of the knot, which in our case is r to the 14, of the variables pi and xi, where pi and xi run from, where I runs from 1 to 7. And for each crossing, you get a contribution, and it's always of the form the exponential of a Lagrangian corresponding to that crossing. And the Lagrangian for each crossing is written down here. So the Lagrangian for each crossing is written in this form. And if you take the Gaussian integration formula from the previous slide and apply it to the to this particular choice of perturbed Gaussian integral, the result will be the one variable reduction of the theta that I talked about before. And similarly, there are formulas for the full theta thing, except the formulas are a bit harder, and the integration is an integration over 6 times the space of edges. And now I can tell you the dream. Okay? So the dream is that there is a similar perturbed Gaussian integral formula for theta, but the integration should not be, so we already have a perturbed Gaussian integral formula for theta with integration over the space of edges, or a space that has one dimension for each edges, and then you multiply by 6. So what I expect is that the integration will be over a space which has 6 times the first homology of the surface. The quadratic Q will be the same as the Seifert-Alexander formula, because you want the denominator to be the Alexander polynomial, except repeated 3 times, 1 for each variable t nu. The perturbation, so the perturbation should be some function on the homology of the Seifert surface. And the point is really, why stop at linking numbers? So you have these cycles representing the homology classes. You can look at higher invariants of these pairs of, or triples or quadruples of cycles. Okay? I don't know, the Massey products, various other low-degree finite type invariants of those homology cycles. I don't quite mean it literally, because there is more information for cycles on a surface. So for example, 2 cycles on a surface can intersect. And for the purpose of computation of the linking numbers, we pushed off one of them and so eliminated the intersection. But maybe the right thing would have been to, rather than push, rather than separate them, just weld them together and get a knotted graph. And then the linking number is actually a fair invariant of a knotted graph. So maybe you can do, so you may need to get some information from the, extra information from the Seifert surface, but the bulk of the thing will be from far away, if you will look at it, it will look like finite, but by low degree finite type invariants of curves on sigma on the Seifert surface. And that's the dream. This is my dream. Okay? Sorry, I mean, if you talk about dream, you know, I don't know what to, okay. What's the evidence? Okay? By the way, I believe in it very strongly. So, I mean, I think, not only I believe in it very strongly, I believe it's a matter of a year or two. Okay? This isn't like the Riemann hypothesis, that like you can believe it or not believe it, and God knows how long it will take. You will see this in a year or two. Okay? Anyway, first of all, the degree of theta is bounded by the genus of the Seifert surface. I suppose here I got the signs correctly. How could you get such a thing? Okay? Theta is a perturbed Gaussian integral over the space of edges. The most reasonable way you can get a genus bound is if it was also a perturbed Gaussian integral over H1. And then the number of variables that will occur will be bounded by the genus, because the variables live in the homology of the surface. And the genus bound will come somehow from that, by basically simple counting. There is also theoretical support from this, from various other perspectives. Yeah, I don't think I want to go there. God, I know this sounds like I'm a lunatic, well, wait. Anyway, why is this dream so sweet? Why do I care telling you about it? Well, first of all, it will allow to prove the genus bound. Okay? And, you know, maybe some topologists one day will want another genus bound, which is sometimes stronger than the genus bounds that you get by other means, by the Alexander polynomial, say. So that's not a little thing. Also, so I mentioned at the beginning that theta has symmetries that we don't understand. In particular, it always has hexagonal symmetry. The formulas don't show it. By the way, the formula for the Alexander polynomial that I've implicitly used in the first talk, namely the determinant of that matrix A, does not see the palindromicity of the Alexander polynomial. The Alexander polynomial is always palindromic. So if you substitute t equals to t inverse, or if you switch the order of the coefficients, you get the same thing. So to see the palindromicity of the Alexander polynomial, the best place to go is to go to a Seifert formula. So I'm expecting that in a similar way, to see the hexagonalicity of the theta invariant, you'll have to go to the theta polynomial. Sorry, to the Seifert formulas. And then, what? Am I out of time?
Sorry, no, my apologies. We haven't had it on for an entire day once before, so.
So the batteries are out?
Yeah, I can just take the body back.
Okay, but probably you all hear me anyway, so maybe I'll just stay without it. Okay? Okay, is it okay?
Yeah.
Sam, is it okay? You're the farthest?
I'm good.
Okay. And then the last bit is, so you know, the Alexander polynomial, I mean, let me argue that the Alexander polynomial gets part of it, a major part of its power from the Seifert formula. So for example, the Alexander polynomial has something to say about ribbon knots. There is the so-called Fox-Milnor theorem, which says that the Alexander polynomial for ribbon knots is of a special form. And one proof of it goes as follows. So first of all, what's a ribbon knot? It's a knot that bounds, it's a red knot that bounds a blue membrane that's allowed to have only one type of singularities, namely the singularities shown here in green. Here is an example of a ribbon knot. And then if you have a ribbon knot, you can make a Seifert surface for it by, well, playing a little game around the singularity. The picture shows the game better than the words that I would use to describe it. The point is that there is a homology cycle here. Now it's marked in green. It's unfortunately the same color of the singularity, but it means something else. So there is a homology cycle here. And in fact, if you have if you have a genus G, Seifert surface that's obtained in this way, it will have G cycles that look like round circles and which make an unlink. And so formulas like so, so the quadratic Q has a very big piece on which it vanishes. Namely, if the two cycles come from among those green homology generators, half the dimension. In the presumed Gaussian, perturbative Gaussian formula, also many things will vanish because, again, it's a formula that's going to depend on invariance of the invariance of the links that are obtained by starting from homology cycles of the Seifert surface, and much of these cycles make the unlink. So you'll have lots of vanishing. So there is the potential that theta has a Fox-Milnor-like theorem, okay? And that will be amazing. That will be just absolutely amazing. I think I'm too confused. You're probably too confused, and I'm definitely too confused to continue telling you how the invariant will be computed. But let me say something. So there is a little bit of Seifert surfaces are a bit misleading because maybe many of you have seen the Seifert algorithm to produce Seifert surfaces. So you take a knot, you find its oriented smoothing, you multiply it by an interval, you glue twisted bands where the crossings were at the top of that cylindrical thing, and you cap the band, okay? That's nice theory. In practice, it's been, 20 years that I've been trying to implement it reasonably on a computer, and I can't. In practice, doing computations with this is nearly impossible. Let me give you a way of quantifying this. Actually, let me start from another story. Okay, so every knot is a braid closure, but that's a complete disaster computationally, because if you have an n-crossing knot, the naive algorithm to present it as a closure of a braid will present it as the closure of a braid with n-squared crossings. And so if your invariant computes in some exponential time, or whatever formula, if your invariant computes in time that's proportional to 10, if you have a 10 crossing knot, then computing it using a braid closure will start from 100, okay? if you're a bit non-naive, you can reduce it to n to the 3/2. But I don't know how to reduce it further. So if you have a knot with n crossings, the smallest braid whose closure is this knot will have n to the 3/2 crossings. And again, if you're talking about knots with 300 crossings, 300 to the 3/2 is worse than science fiction. Okay? There is a similar thing with the Seifert surface, with the Seifert algorithm. So again, this looks nice and clean, but how would you present a Seifert surface on a computer? So, because you want to do it, because you want to do computations with it, right? So one way to do it is to say, well, every genus G surface is the closure, sorry, not the closure, the thickening of a graph that looks like this. So like G double hump camels, and if you thicken each, like basically this becomes a genus G surface. So you can say, I will represent my Seifert surface by a knotted, by embedded in R3, right, by a knotted G hump camel. G, yeah? And, but then you can ask, what is the complexity of this graph? Okay, of this knotted graph. And the answer is that if you do the Seifert algorithm, and then use the theorem, the classification theorem of surfaces to convert the surface that you would get from here to this shape, you'll get roughly n squared crossings. So you lose a great deal in efficiency. So I still don't know how to present Seifert surfaces properly on a computer and how to manage them efficiently. But I have an alternative, and if I had more time, I would tell you about it, but I don't have more time, and I'm too confused anyway, and it's all about dreams, so hopefully at some point in the future. Sorry. Yes, Sukarit?
Yeah, so the Alexandric polynomial can also be computed by non-orientable surfaces, right? Like by Goritz matrix. You don't have to have a Seifert surface. You can also take a non-orientable surface, which is sometimes computationally better. Like for alternating knots, it's better. So do you have a non-orientable surface dream?
I don't, but you know, thanks for the idea.
Because it's computationally often better, like for alternating knots. It's generally
Thanks for the idea. No, I do not have a dream along these lines.
So for the symmetry of the Alexander polynomial, there is also this like Milnor's argument to some sort of Poincare duality for the Reidemeister torsion. So couldn't there be such an argument with the hexagonal symmetry?
So that would be an even better dream, an even greater dream to try to interpret these formulas that you get from perturbed Gaussian integration in terms of the likes of that, so Reidemeister torsion. I have no comments, I have no ideas. Like the Seifert dream is close to reality. That would be too speculative for me to comment on.
Okay.
I must have asked you this before, right? But you're counting some theta graphs, and the theta graph itself has some symmetry. And does that factor into any of this?
First of all, well, okay, the answer is no, because the coefficients lose this symmetry. So I'm counting theta graphs in some sense with coefficients, but the coefficients just look like complete random mess.
Sorry, I should have asked this question earlier, but could I ask you to explain this, just for the Alexander formula, what this integral formula is saying?
Sorry?
Just for the Alexander polynomial, what this integral formula is saying. Well, what does this mean? Sorry.
This, the integral formula? So there is a So if you look at, I don't know, books in analysis, on analysis, you will find that the integral of e to the minus 1/2 xa lambda ab xb, and I'm using the Einstein summation convention, relative to the product of all the dxa's, is equal to, there is a determinant formula for the answer. So the answer is, what is it? 2 pi to the number of variables over 2 divided by the determinant of this matrix lambda. The determinant of this matrix lambda. So basically that's what I'm using here, except here I double the number of variables, so instead of the determinant to, oops, sorry, this should be the determinant to the power 1/2. So the square root of the determinant. But here I double the number of variables, so it becomes the determinant to the power -1 rather than minus to the 1/2. But it's I'm not sure what else to say. It's a standard formula in analysis.
So H1 sigma is really H1 sigma R, and this is not like a discrete sum, but it's an actual integral.
Sorry?
So H1 sigma is really H1 sigma R, and this is a real integral and not some like discrete sum or, sorry.
Yeah, it's a vector space.
Okay.
Cool.
Yeah, it's a vector space and it's an integral over a vector space. And it's H1 with real coefficients. And in some sense, it's a lie. Because you see, this formula is true. What I wrote here is correct, provided this matrix is positive definite. But you can declare that this integral is equal to that, even if the matrix is not positive definite. You can just analytically continue. Likewise, the perturbed version is a true statement given some convergence conditions, but you can just make the right-hand side be the definition of the left-hand side if the convergence conditions don't hold. And the point is that all the tools still hold. The main tool being Fubini's theorem. It turns out that all you need in order to prove invariance is Fubini's theorem. And there is a Fubini's theorem for the combinatorial definition. So it's really combinatorics. It's not really about integration. I really don't care about integration. Okay, sorry if that was horrible. That's not going to stop me from putting it on the internet. If there are enough videos here, there can be lousy math talks too.
What's the intro again?